In February 2018, GitHub faced one of the largest DDoS attacks in its history. The attack, peaking at 1.35 terabits per second, targeted GitHub Pages, a service hosting static websites and projects on GitHub. Fast forward to August 2020, Twitter encountered a massive DDoS attack, causing platform unavailability for users worldwide for several hours. In January 2021, the Microsoft Xbox Live Network experienced a significant DDoS attack, temporarily rendering the online service inaccessible to many gamers. These incidents highlight that even big, tech-savvy companies are not immune to DDoS attacks. Such attacks can have serious consequences on the availability of online services and potentially harm a company's reputation. Do you want to know how DDoS attacks work? If yes, let's dive in. So, what is DDoS? Let's start with a simple example. Imagine a small shop with only one cashier. The shop can serve one customer per minute. However, if the number of customers increases, the cashier won't be able to handle them all, and a crowd will form at the entrance due to limited space inside. Sound familiar? Now, replace the shop with a server and the crowd with users' computers sending requests to the server. What do we have? It's a typical cyber attack known as distributed denial of service or simply DDoS. DDoS is a type of cyber attack where attackers try to make a resource inaccessible to legitimate users by overwhelming it or causing malfunctions. The core idea of a DDoS attack is to deplete the resources required for the normal functioning of the target resource. So, you've grasped the concept that a server attack happens with a coordinated effort from multiple network devices simultaneously. But how does that even happen? Is it possible? Absolutely, and let me tell you how. Imagine a regular computer or laptop owned by an everyday user, along with various other network devices. This could be a home router, smart home devices, IP cameras, and so on. A hacker can infiltrate these devices, installing a backdoor that partially or fully controls the compromised devices. The installed backdoor turns these devices into a compliant army of bots, forming what we call a botnet. At any given moment, the hacker can send commands to the botnet, instructing it to launch an attack on a particular server. The bots will then start generating massive traffic, leading to a sudden surge in requests. As a result, the targeted server becomes overwhelmed and crashes. Now that you understand what DDoS is, let's delve into the various types of attacks that exist. If we look at the 7-layer OSI model, DDoS attacks mainly occur at the network, transport, and application layers. Let's break down each type individually. At the network layer or layer 3, hackers leverage the ICMP protocol to generate a massive number of echo requests. The principle is simple. Host A sends an echo request to host B. Upon receiving the request, the host must process it and send a response. This is where hackers exploit by inundating victims with a huge number of requests, forcing them to expend resources processing each one. Let's demonstrate this attack using 2 Kali machines as the attackers and a Windows machine as the victim. On the victim machine, let's open the task manager for clarity. Notice there's currently no traffic. There are numerous programs on Kali for conducting such tests, including Ping 3, Slow HTTP Test, GoldenEye, Low Orbit Ion Cannon, and many others. On the attacking machine, I'll use the Ping 3 utility, where the ICMP option signifies the ICMP protocol mode. C indicates the number of packets to send, Flood denotes flood mode, and Data indicates the size of data to transmit. I intentionally increase the packet size to ensure they're fragmented, thus increasing the total number of packets. Now, let's execute the command. As you can see, the volume of network traffic has increased. Let's launch the attack from the second Kali machine. You can see that the traffic volume has nearly doubled. Now, imagine an entire army of zombie bots generating similar traffic. At the transport layer or layer 4, hackers utilize UDP and TCP protocols. Let's first examine how the UDP protocol is used. The principle of operation is as follows. Host A sends a UDP request to host B on port 300. Host B then checks if it has an active program or service using port 300. If such a service exists, it sends a corresponding response. If not, the system generates an ICMP response destination unreachable. Now, imagine a hacker sending thousands of requests with random ports, forcing the attacked host to process all requests. To simulate UDP flood, we can also use Ping 3. With the dest port option, we can specify a specific port or a range. And once again, we observe the network traffic increasing. Let's delve into the TCP protocol. This protocol is quite intricate and is always in play whenever you need to establish and maintain a connection with a remote host. TCP follows a three-way handshake to establish connections. For instance, if there's a web server running on remote host B, which uses port 80, host A sends the initial connection request. If everything is in order, host B acknowledges its readiness to connect. Host A, in turn, confirms the connection, thus establishing it. However, if the web service isn't running on host B, and host A attempts to establish a connection, host B would refuse it. Now, let's talk about how attacks work. A hacker sends multiple requests to a specific port. The remote host acknowledges readiness to connect, but the hacker doesn't respond, leaving the server with half-open connections waiting for confirmation. Consequently, memory is depleted, and eventually, the server stops responding to requests and processing already established connections. But here's the question: what happens to the hacker's computer or bot when it receives responses from the attack servers? In such attacks, hackers or bots spoof their IP addresses to random ones, ensuring they never receive responses from the attacked hosts. Let's examine the TCP SYN Flood attack using two Kali machines. One acts as the attacker, while the other is the victim. To simulate the attack, we'll start a web server on the victim machine. Now, using the netstat utility, let's check the current TCP connections. As you can see, there are no active connections now. On the attacking machine, we'll again run ping 3, but with slightly different parameters. The SYN option enables TCP SYN mode, and will specify port 80 as the destination port. Let's execute the command and observe what happens on the victim machine. Run the netstat command again. This time we see a huge list of half-open connections. TCP SYN Flood has a dual effect. It sends a large stream of packets to the targeted server, clogging communication channels, while simultaneously depleting server resources to handle and support half-open connections. At the application layer or layer 7, hackers can execute DNS Amplification and HTTP Flood attacks. Let's delve into how the DNS protocol operates. Imagine a web application like good-site.com, hosted on different servers across various countries, each with its own IP address. To access the site, we simply type its URL without needing to know all its IP addresses, which is convenient, isn't it? However, our computer does need the IP address, and this is where the DNS server acts as an intermediary. It stores IP address records and provides them upon request. Some websites, however, may have numerous subdomains and addresses stored in DNS servers. Hence, the size of the response message can be tens or even hundreds of times larger than the hacker's initial request, creating an amplification effect. By substituting the sender's IP address with the victim's address in their request and sending it to multiple DNS servers, the hacker compels the DNS servers to transmit a large volume of data. The attacked host is then overwhelmed with processing this substantial data flow, inevitably rendering it incapacitated. Currently, several botnets are known, including the well-known Mirai, Satori, Tsunami, IoT Reaper, Nital, and so forth. While botnets are used legitimately for stress testing network resilience, unfortunately, they're also leveraged for malicious purposes, with individuals purchasing DDoS services of any volume and duration from the darknet.